All right, so let us take a look. We'll get started here. I'll put my face over here, and then we'll open up our studio. Let me open up our notes. So these are, I'll just quickly go through the notes I posted on numeric derivatives. And then today we're going to take a look at optimization. Okay, so derivative approximation. So Newton-Raphson method makes use of a derivative, right? So I think you guys had to figure this out. And then, okay, so one common thing I'm seeing on, what do you call it? On CampusWire is that when you write a function, don't call one of your functions C, okay? Because if you do that, it's going to overwrite the all very important regular C combined function where you put numbers together and make a vector. So if you make a function called C to compute some value, and you're gonna run into problems. So don't do that. Okay. So anyway, what you're gonna do is Newton-Raphson, you create a function, and then that function should return two values: the value of the function itself and the value of the derivative at that point. Okay. And I think the functions I gave you are easy enough. Okay, and derivation is generally a lot easier than integration, but sometimes taking the derivative can be hard, especially with chain rule and stuff like that. So, so this is one way to get the derivative without actually calculating the derivative. Okay, doing it analytically. Okay, so the derivative gives you the slope of the tangent line. Okay, and basically we're just using this idea that the derivative is equal to this thing as h goes to 0, and we're just going to use a tiny little value of h, okay? And so we take a small value of h, we're going to calculate the function at a plus h, we subtract off the value of the function at a, we divide by h itself, and that's going to give us an approximation of the derivative, right? So if our function was log of x minus e to the negative x, okay, I just take x and then I add h to it, log of x plus h, minus e to the negative of x plus h, okay? And then I take the difference between f of x plus h minus f of x, okay, that's the difference, and I divide by h, okay? And that's going to give me an approximation to the derivative, okay? So if I take the approximate value, I get 0.2067379236669, and then the actual value that we calculated using math, okay, the actual value is pretty much the same. Maybe the last 1, 2, 3, 4, 5 digits are different, okay, so the last 5 digits, but the first 7, 1, 2, 3, 4, 5, 6, 7, the first 7 digits are the same, the last 5 are off, okay, which is pretty good, okay. All right, and then the other thing is here I added 1e to the negative 6. I could also add a negative. Okay, 1e to the negative 6, but a negative version. So I have log of x, e to the negative x, and then I do log of x plus h, negative e to the x plus h. I take that difference, okay? And then what we see is that the true value is this. And then if I take the negative side and the positive side, generally, if there's any curvature, generally one will be a little too steep and one will be a little too shallow, okay? Because you come in from the left and it's coming like this, and then you come in from the right, it's going the other way. And so this is grossly exaggerated, but the true value is the dotted, okay? And then coming in from the right, it's a little too shallow. Coming in from the left, it's a little too steep. So we're going to kind of take the average of these two things, and then so I do on the right side I do f of x plus h, and then on the left I have f of x minus h. Okay, so here's this, and then I take the difference between the plus and the minus, and I divide by 2 times h. And this is my approximation, okay? And so here it is accurate up to 10 digits, and only the last 2 digits are off, okay? So that's pretty good, okay? And I think we leave it kind of there. I generalize this and I say, okay, here's a function of a function. So one of the arguments that comes in will be some generic function. and then you say, what is the derivative at this location x? And you just say, here's the x value, x minus h. On the right side, it will be x plus h. And we do function on the right, function on the left. Take the difference between those, divide by 2 times h. Okay, and then so you can plug in. So if this is our function, we can do this and it works. Okay, if I just have some arbitrary function x squared, okay, the true derivative of x squared is, at 5 is 2x, so that's going to be 10. Okay, and if I do the approximation, I get something very, very close to 10. Okay, off by 1, 2, 3, 4, 5, 6, 7, 8, accurate up to the first 8 digits. Okay, so this is what we have. You have to be careful about floating point numbers. Okay, so you might say like, well, let's get the smallest h as possible. Okay, but if you go too small, you run into the limits of floating point approximation, right? And so you run into some problems. And so here I'm using h, 10 to the negative 5, 10 to the negative 6, 10 to the negative 7. And we can see these are all performing pretty well, okay? The true value being 10, and we're getting numbers quite close to 10 as far as approximations go. But you can see when I get too small, okay, now my accuracy starts end up being quite a bit off. I get 9.7, 8.88, and if I try to do 10 to the negative 16, it zeroes out, okay? So obviously that's something we don't want to do. Okay, is that all right for taking approximating a derivative? Obviously, if taking the derivative is simple and straightforward enough to do it analytically, do it analytically, right? All of these numeric methods are if the analytic method is too hard, okay? Kind of comes with that thing, right? If the analytic method is too hard or too time consuming, then a numeric approximation is acceptable. But if you can do the analytic method, use the analytic method, okay? All right, so today I want to, let me, use this pen here. All right, so here we go. I know, so I'm writing on the screen. Okay, so now we're going to talk numeric optimization, right? Okay, so if you want to take out paper and pencil, you can, or you can just watch and follow along. Okay, so numeric optimization is all about basically finding a local min or max. Okay. Often the problems are framed as finding a local minimum, and then if you want to use it to find a local maximum, you just find the local minimum of the negative of the function. Okay, so a lot of okay, so a lot of algorithms are written for finding a local minimum of f of x, and then to find a local max, just find the min of negative f of x. Okay, so that's what we do. So this is 102A. I don't know what this is. This is week 8. Monday. All right. Okay. So there's the first set that we're going to look at is going to be derivative-based optimization. Okay, and this is simple and straightforward, right? So in calculus, you learn for a continuous function, a local min or local max will have a derivative equal to what? Equal to 0, right? So in calculus, if there's a local min or local max, okay, the derivative at this location equals 0. Okay, so so this is it. We just apply this to find local mins and local maxes, right? So basically, so last week we learned all of these root finding methods, okay? So root finding methods helps us find where some function is equal to 0, okay? And then so all we have to do is we just take the derivative of that function and then we apply a root finding method to it, and then we find out where the derivative is equal to 0, and that's pretty much it, okay? So conceptually, very, very simple, right? Okay, so last week we learned root finding methods. To find where f of x equals 0, okay? So to optimize a function, as in find a local min or local max, okay, basically step 1, find the derivative. Find the derivative of a function. Okay. 2, apply a root finding method. To the derivative, okay, and this this results in gives us critical points. And then we'll just check the critical points to see if they are local mins or local maxes, right? Is that okay? Does that make sense? So the hard part is finding the derivative, okay? I mean, honestly, if it's easy to find the derivative, it's probably not too hard to find where the derivative is equal to 0, right? So you just think back to your days of calc. Was it calc 1 when you would do this? Okay, calc 1, you take the derivative of the function, you set the derivative equal to 0, you check those critical points to see if they're local mins or local maxes, okay? Yeah, that's it, okay? That's it. So, probably the most commonly used one, though, will be Newton-Raphson. I mean, any of those root finding methods will work. You apply any of the root finding methods, so whether that's fixed point, Newton-Raphson, secant, bisection, you apply it to the derivative to find a critical point where it's equal to 0, and that'll work, okay? But probably the most common is going to be Newton-Raphson. For basically optimization. right? Okay, so we wish to optimize f of x, okay? And then, so this means, this becomes, we wish to find the roots of f prime of x, okay? So how would we find the roots of f prime of x? Okay, so then our algorithm, okay, so here, let me just pull up the notes for root finding for Newton-Raphson method. Okay, basically, you know, it's x at time n plus 1 is f of x minus f prime of x, but now your f is f prime itself. Okay, so this is basically what we're going to do, right? Start at some initial value, and we're going to apply this to find the roots. This is finding the roots of f, so finding the roots of f prime. Okay, so we're going to start at some initial guess x0, okay, and then iteratively find the next value, okay. X at time n plus 1 is going to equal x at time n minus, okay, so finding the roots of x is this, okay. This would be finding the roots of f, and then so to find the roots of f prime, I'm going to just change f to f prime, and f prime becomes f double prime. Is that okay? And this will give you a critical value, okay? And that's it. Okay, so again, here are the, this is the algorithm for finding the roots of f, and now we want to find the roots of f prime, so I'm just replacing f with f prime, and I'm replacing f prime with f double prime, okay? So, you know, what does that mean? It means f has to be twice differentiable, okay? So I guess requirements. Twice differentiable, and then f double prime of xn cannot equal 0 for the xn's that we check. Okay, it can be 0 in certain locations, just not at the locations that happen to be in our path, right? Okay. All right. I don't know what else to say. Okay, so one thing is you might say, well, you know what? What's the point, right? I have to take the derivative. Like, I don't want to take derivatives. I'm a stats major, not a math major. I don't know what you would say, right? Don't say that, okay? You got to be able to do a little bit of math here, okay? But you know, taking the derivative might be hard. Taking the second derivative might be hard, okay? But what do we have? We have an approximation, right? We have a method to approximate taking the derivative, okay? Which means if I apply it twice, I have a method to approximate the second derivative, okay? And it works just as fine, right? So remember, we have derivative approximation. Okay, which basically says, you know, I don't know what I'm going to call this, f prime approx is a function of some function, and x and h kind of equaling 1 e to the negative 5 or whatever, you know, some value. And then on the left, I do take the function of x minus h. On the right, take the function x plus h, and then we're going to do the right minus the left divided by 2 times h, okay? This is what we do, okay? And then so if I have, if I do this, right? Let's say I have some function, right? F is going to be some function of x. Okay. All right, so you write something, okay, of x. Yes? ftn. Just some arbitrary function, right? Just there, this is a function, but then this is a user created function, okay? A user created function, and so whatever this could be sine of x, it could be x cubed minus 2x or whatever it is, okay? It doesn't matter. Just this is some user defined function. This is a function that you create. Log of x minus e to the negative x, whatever it is, okay? And we're just calculating that function at x minus h, that function at x plus h. And we just say, how much did it change versus the size of h, okay? All right, and then so anyway, you have that thing. And we can apply it here. And the idea here is that we might not know the mathematical specification of the function, okay? But what is a function? It's just, it takes an input, okay? Here's our mystery function box. And then it spits out an output, okay? So it doesn't matter. It doesn't matter if we don't know what's happening inside the box, okay? I'm just taking an input and it spits out an output. And I can do this for derivatives. I can do this for the original function value. It's fine, okay? Again, all of this comes with a caveat. If doing the analytic derivative is easy, do the analytic derivative, okay? Maybe like in a homework exercise, I make you do something silly where you have to do this thing even though the analytic derivative is super easy and finding the optimum and is super easy, okay? But in general, right, if the analytic way is easy, just do the analytic way, okay? All right, so here, let me make this bigger for you guys to read. Appearance, 150, let's do that. Okay, so here I have some function. 0.25 x to the fourth minus 0.5 x squared, okay? So I have f of x. Oh, I called it g of x. All right, sorry. I hope the change of letters doesn't confuse you, okay? Okay, g of x is x to the fourth. Wait, what is it? I think it's 1/4 x to the fourth minus 1/2 x squared, okay? So, I mean, this is super easy, right? So if we had to, we could do g prime of x would be, you know, we take the 4 and we get x cubed minus, and we take the 2 and we get x squared, okay? And then g double prime would be 3x minus, I'm sorry, 3x squared minus 2x, okay? So this is, yeah. Did I mess something up? Oh, yeah, thank you. Okay, even better, all right. Okay, so x cubed, yeah, see? It's so easy, you make mistakes, right? Okay, this kind of stuff happens all the time. All right, so anyway, g prime and g double prime, this is easy, right? But let's say, like, I don't know, you dropped Math 31A or something, and you never learned this, even though I think this is like your first day of class. So what do we do, right? Okay, somehow you have an understanding of numeric derivative approximation, so it's fine, okay? So we do this, and then let's just plot this, all right? So here's G, and here's the plot. Okay, this is, okay, so this is what the function looks like, and we want to find, this is just our horizontal axis, and we want to find some like local mins and local maxes, okay? All right, so here's my numeric derivative approximation. We take the function, we're going to do x minus h, this is on the left, this is on the right. We take the function at the right minus function at the left divided by 2 times h, we return that value, okay? So I can say, okay, what is the derivative at this location, 1.5, okay? And I get 1.875, and I can compare that, well, what if I plug in 1.5 into this, right? G prime of 1.5, and I do 1.5 cubed minus 1.5, and indeed, okay, I get the same value. So this is taking the approximation, and this is the actual thing, okay? To kind of just simplify things, so right now the function, as I have to do it, I have to specify the function g plus the location, okay? I'm going to just take the function and just say give me back, and assume g is always being used, okay? And do this, all right? So here I can just say what is the numeric g prime of 1.5, and it just gives me 1.875. So now I've simplified it just to say one input in and one input out. I don't have to continually specify g is the function that I want, okay? All right, and then so I could, so here I calculate this for my entire vector x, which goes from negative 1.8 to positive 1.8, and I'll plot this, okay? So this is what the derivative looks like, okay? And what do we see? We see at the local min, the derivative is equal to 0. At the local max, the derivative equals 0. At the local min here, the derivative equals 0 as well, okay? And then where there's an inflection point, that's where the, something happened. This thing is frozen. Hang on. do anything. That's not, I don't want that. All right. Oh, all right, okay. I guess it rolls the screen back up when it reboots itself. Okay. What was I saying? All right. Oh, okay. So anyway, this is what the derivative looks like at the inflection points right here. That's where you have an inflection point. That's where the derivative has a local max or local min, right? That's when it changes from, what is it, concave up to concave down, things like that. Okay. So here, the actual derivative is x cubed minus x, okay? And I can calculate the actual derivative. And here, I'm just plotting the actual derivative over our estimated derivative, and we see that they're like the same. And if I do all equal, it comes back true, okay? So that's a good sign, okay? Now, remember, so I just have a numeric approximation for the derivative. And I can just say, take the derivative of that, okay? Take my numeric approximation. And so all it's doing is it's just taking the numeric derivative, and it's going to calculate the numeric derivative at x plus minus h, and the numeric derivative at x plus h, okay? So the numeric derivative, again, is just an approximation, okay? But it's going to use that approximate value and calculate it at x minus h and x plus h, okay? Because on this plot, you know, we have the numeric derivative in blue, and it's just, it doesn't have any mathematical understanding. It's just going to say, when I plug in -1, it gives me this value, and when I plug in -0.999, it gives me this value, and when I plug in -1.00001, it gives me a slightly different value, okay? And then it just takes the difference between that and calculates a slope there, okay? So there's no, it doesn't matter that it doesn't have a mathematical understanding behind it. It's just going to do the calculation. So we just say, take the numeric derivative approximation here of this, and we'll call that g double prime, okay? And then so I do that, and I plot, and I get g double prime, and indeed that sure looks like 3x squared minus 1, okay? And here I can calculate the actual. I can do 3x squared minus 1 and see, you know, what does that look like, okay? And I just plot that on top. And again, we can see it looks like the actual and the approximation are pretty much the same, okay? And if I ask, are the actual values and the approximate values the same, okay? They're not exactly the same. They're off by 10 to the negative 8, okay, on average. So there's a little bit of difference, but you know, for most, this means it's accurate up to around 7 decimal places, okay? And so for most of our needs, that's good enough, okay? And so now that I'm able to have the f and f double prime, I can just apply, you know, Newton-Raphson method or any of these root finding methods that I need to do, okay? All right, I got a couple minutes left. In your homework, I have you guys look at golden section search, okay? Where is that golden section search video? Okay. Golden section search is kind of like bisection method, but it's for optimization, okay? And it takes advantage of this neat phenomenon, okay? So, okay, let's say you have some function that looks like this, okay? And you want to find You want to find this optimum value, okay? So here we're going to say this is the left bound, this is the right bound. And I forgot how we basically have two values in the middle here, okay? And one of these is A and one of these is B, and I just want to be consistent in how I gave you your homework. And I guess depending on which page you read, okay, so you have the, okay, so I guess one's called the lower and one is the upper, okay? All right, so this will be lower and this will be our upper bound, okay? And then here, I've got, I'm gonna call this x1 and this x2, okay? And when we do this, okay, so we know that there is a minimum, okay? Between the lower and upper upper bounds. Okay, I ran out of battery. That's what's going on. Okay. And what we do is we calculate the value of the function at x1 and x2. So we calculate this, and we calculate this, okay? And what we find, so here's f of x1, here's f of x2, okay? And we find that f of x2 is less than f of x1, okay? And so what this tells us, all right, is that, okay, because we know there's a minimum between the lower and the upper bounds, okay, and I guess there's, one minimum, I should say. If we say there's one minimum between the lower and upper bounds, when this happens, okay, this tells me that the minimum cannot be over here. Okay, how can I be confident, right? So, okay, because, and the reason why is because we know that there's a value to the left between f of x1 and the lower bound that's lower than f of x1, okay? It's f of x2. So we know that the lower value, the minimum, has to be on this side. It can't be over here because we already know that there's a value over here that's lower than over here. So we can completely eliminate this, okay? And so I can throw this side away, all right? And here's the amazing thing, okay, is that because of the golden ratio, okay, so if I say this is from 0 to 100, this distance is around 61.8%, okay, and then it's around 61.8% this way, okay. And okay, so this is a bad illustration, but after, okay, I have no idea. Today, all of this stuff is giving me a hard time. All right. Okay, not a good picture, okay, but after I eliminate this side, this thing, okay, this is my new lower bound and this is my new upper bound. This again, terrible picture. This ends up being 61.8% of the way from the lower to the upper bound, okay? And I apologize, this is, my picture is bad. Okay, my picture is bad. Let me, there's got to be a better golden section search, okay? I'll post a better image of this, okay? All right, so this looks a little bit better, okay? So if this is 0 and this is 100, this is 60 around X, this location to this dotted location is around 62% of the way from here to here. And then after you eliminate this side, this line that you calculated here is 62% of the way, 61.8% of the way from here to the new right bound, okay? And that's just a feature of the golden ratio, is that you can kind of keep doing this. And that that allows you to reuse a value that you used earlier, okay? So rather than having to recalculate all of this. I guess we can continue expanding on this on Wednesday, but we'll see you then. Okay.